We have to know if Dr. Graham is able to teach courses, like concurrent with his role. Or do you know if Dr. Graham is able to teach courses while he's running it?
Oh, yes. I think he might be teaching now. So,
You know, to see if he was interested in like a K-3 course.
right. Would be good.
Do you know offhand if he's run anything like that in the past?
No, I don't, but I'm hoping that we'll have a meeting after the algebra seminar sometime. Students usually do that.
Have you seen the email chain that we're talking about?
Have I seen the email chain?
Yeah, they sent out an email to the algebra listener today. They started discussing in an email chain instead of a meeting.
No, we should set up a meeting. Just, otherwise, we're going to miss certain points. No, we should set up a meeting.
Some suggestions of all beyond the topic schools. Maybe one between graph theory and low dimensional topology.
Yeah, I mean, those are good ideas, but I mean, basically, they need to be presented at a meeting so everybody, knows what's going on. If you decide not to come to the meeting, well, that's your choice. Okay, let's see. I guess we can start. So we were talking about the Bott-Borel-Weil theorem. All right, so actually I stated the Bott-Borel-Weil for characteristic 0 last time. And so today we're going to work towards a generalization of the Bott-Borel-Weil. We'll actually prove it for the characteristic 0 case and the generalization. So let me recall a few items. So let's say delta, this was the set of simple roots. And then I pick out an alpha inside of delta. And what we can do is we can form a parabolic subalgebra, P alpha, which is L alpha, semi-direct product U alpha. Okay. And so this is what's called a Levy decomposition. And so the picture kind of looks like this, like in GLN. You're taking this sort of like 2 by 2 sort of block matrix, and then you're going to add the torus to it. I'll just kind of denote that by this. So this part is L alpha here. And you take this sort of upper triangular part. The U alpha part over here. So you're just extending the Borel by a one-dimensional, variety in some sense. This one-dimensional thing kind of sticks out. Okay, so we have set up where we have B, P alpha, and G, okay, where G is your reductive algebraic group. All right, now I'm not sure if we need this formula today, but let me just recall the dot action. So we will actually need the dot action today. All right, so we have W, which is the Weil group. And so we have the ordinary action of the Weil group on the weights. So W acts on the integral weights x of t. And so now what we're going to do is we're going to shift the action. So the dot action is the following: W dot lambda. This is equal to the ordinary action on lambda plus rho, and then we're going to subtract off rho from that. So rho, we have some positive roots. Or you can also think about it as the sum of the fundamental weights. And we have a formula that we worked out last time. So we take S alpha dot lambda. This is lambda minus lambda alpha check. So lambda plus rho alpha. This is a rho, apply. This is a formula that you can work out just by using this and the reflection formula. Okay, any questions on this? All right, so what I want to do next is I want to state a proposition, and I'll sort of indicate certain parts of the proposition. And we're not going to prove this, but I just want to give you some indication of how this works. So here's the proposition. So let alpha be a simple root, and let's say lambda is a weight. Okay, so part one, U alpha acts trivially on induction from E to P alpha of lambda. Now, the reason why this is true is because U alpha is part of the semi-direct product. And if you sort of go through the definition of the action, U alpha, you will see that that's true. Okay. And then this actually holds more generally. This is any parabolic up here. And this is the unipotent radical of the parabolic, then this statement is also true. Okay, so B, if I take lambda alpha check, this is positive. Okay, so it's sort of dominant with respect to this root alpha. Okay. So then type of Kemp's vanishing theorem holds. So I induction from B to P alpha of lambda equals 0 for I bigger than or equal to 0. Okay, so this is a kind of a Kemp's vanishing theorem for P alpha. Okay, and this is kind of what you expect too. So the dimension of the induced module from B to P alpha of lambda. So this is the dominant weight, right, with respect to alpha. This is like an SL2 module. SL2 kind of extended. So what do you think the dimension should be? It should just be this inner product plus 1. Okay, so this is just R plus 1. Okay, so this is just kind of the SL2 theory you've seen, but just for this P alpha. Okay. All right, good. Now, what we're doing is we're sort of analyzing things on SL2. So this is just SL2 theory sort of extended to this parabolic. So C, if lambda alpha check is equal to -1, so you're sort of in this neutral zone. So then if you take R dot induction from B to P alpha of lambda, you're always going to get 0. Okay, so for anything you put dot in, 0 and 1. Okay, good. So D, now what cases have we handled? We handled the dominant case. We've handled the case when it's -1. So we have to handle the case when lambda alpha check is less than or equal to -2. So lambda alpha check less than or equal to -2. Then we know that the higher cohomologies, or the cohomologies of B and P alpha of lambda are 0 for I not equal to 1. Okay, so that's the first thing you could say. And we already know it's true for I equals 0 just because of we know that it has to be dominant in order for this to be for this to light up when I is equal to 0. So this one's a little bit more general. And it turns out the R1 case from B to P alpha of lambda, this has dimension. R plus 1 dimensional module. Okay. Now, in the proof of this, it's just working with the distribution algebra. That's what the proof is. And let me make a little bit of a note here. So when do we get things which are not equal to 0? Right here and right here. Okay. And so you can identify what these modules are. So this is induction from B to P alpha of lambda. So this is the case when you have a dominant weight with respect to this. Okay. So this is the arithmetric power of the natural two-dimensional representation. And then finally, when you take R1 induction from B to P alpha lambda, this turns out to be the dual of this thing. Okay. So this is when lambda alpha check is less than or equal to -2. Excuse me. I have to define what R is here. Let's see. Right. Let's see. It's probably in here. Let me just see this. Okay, so if this is true, let's see. What is R going to be? Okay, let's see. Okay, let me think about this for a second. So if you take this to be equal to -2, okay, so then I think you get the dual of the natural representation. Okay. So -3, you can 2 of these stuff. Okay. Yeah. So now let's write out the dimension. So this S3 would be small. Okay. And so the dimension here is 2, 3, 4. Okay, so I think it's just the negative, right? So here R is equal to, careful. So the dimension is this. The R corresponds to the thing up on top. So I think you just take the absolute value of this minus. Okay, so I think that's the correspondence. Okay, so that's how you can do this. So I think I'll mention that, you know, in this, there's what's called surduality, which we'll talk about a little bit later. People kind of know about this. This is what's really happening. So H1 at lambda is equal to H0 minus lambda plus 2. Okay, so there's a duality between H0s and H1s, and then you have to use this weight plus 2 in order to get that. Okay, any questions on this so far? So this is the A1 or SL2 theory that we have. Okay. So now let me mention a corollary. So once you actually have this, you can actually break this out in a slightly different way. So here's the corollary. Okay. So again, let alpha be a simple group with your weight, and let's assume that we have something which is dominant with respect to this alpha. So if the characteristic of the field is 0, then we know that the induced modules will be irreducible modules, and they'll be sort of self-dual. So then induction from B to P alpha of lambda equal to R1 induction from B to P alpha of S alpha dot lambda. Okay, so this kind of indicates sort of Bott-Borel-Weil for this SL2. Now, in characteristic P, these modules are not necessarily irreducible anymore. But it turns out that, you know, if you restrict the conditions on your weight, then you can still say something. All right. So let me make a characteristic P statement. Okay, so B, if characteristic is P, and if there exists S and an M with, okay, so first of all, the S has to be between 0 and P, and the weight is of the form S P to the M minus 1. Now, these weights, later on, we'll actually look at modules of these particular weights, and these are kind of called Steinberg weights. So this Steinberg module is quite an important module of representation here. And so for this Steinberg weight, so I guess one way to think about this is I kind of do a picture like this, right? With this being minus rho, which is minus 1 here. And this is like P minus 1. That's the first hyperplane via the affine Weil group. There's 2P minus 1. So you have these hyperplanes that occur at these levels. Right? And so these weights are precisely the ones that occur at these hyperplanes. And so it turns out that for weights which are on these hyperplanes, these modules are irreducible. So you still have the same isomorphism going on. So if this, then induction from B to P alpha is R1 induction from B to P alpha of S alpha. Okay. All right, any questions on this so far?
What's the bottom right diagram?
This is minus rho. Okay. So later on, we'll see that the composition factors for these induced modules and also the other ones, you have to have things which are linked under this action of the affine model.
I was also going to ask about RA here.
Yeah.
Is it possible to run this backwards? Like if you're trying to find R, like, could you have an S alpha inverse on the left-hand side? I guess is what I'm asking.
S alpha inverse on this side. Then I think what will happen in this condition is that this will be 0. Okay. Because it's non-dominant.
Gotcha. Okay.
Yeah, if you take a lambda over here, you take S alpha. Yeah. Good. Okay, other questions? All right, now we've done everything for SO2. Now what we want to do is we want to sort of bootstrap our way up to the entire group. So the way we're going to do that is we're going to use a spectral sequence. So let me put the spectral sequence up here, and then I'll put the stability theorem, and then we'll use the spectral sequence in proof. Okay, so there's the spectral sequence. All right, so this spectral sequence is a Grothendieck spectral sequence. It's obtained by taking the composition of 2 left exact functors, and one of these functors takes injective objects to acyclic objects. So it's a standard construction using the Grothendieck setup. Okay. So I mentioned this last time. So you take Ri induction from P alpha to G. And then you take Rj induction from B to P alpha. Okay, so now you can do this for any parabolic you want, but we're just going to do it for this one for now. All right. So you're looking at the composition of induction from B to P alpha and induction from P alpha to G. And this converges to the higher right derived functors of the composition, but the composition is just going to be induction from B to G by the transitivity of induction. So this is R I plus J induction from B to G of alpha. Okay, so as you can see, we can get to sort of our desired target. It's the abutment of this spectral sequence. Now, as I mentioned, this is first quadrant. So this is the y-axis down here, and this is the j-axis over here. Okay? And one thing to note is that there's what's called a Grothendieck vanishing theorem, which means that this vanishes above the dimension of P alpha over G. So let me state that as a fact. Good. Okay, let me just put this in a little box over here. Okay. So when I take Rj induction from B to P alpha, lambda, this is 0 for J bigger than or equal to the dimension of P alpha over B. Actually, strictly bigger. But when you take P alpha over B, that's 1. So this is 1. Okay. So for J bigger than or equal, bigger than 1, we don't have these terms. So this spectral sequence only lies on 1 line. Okay, so above 2 and greater, everything is going to be 0. So let me draw that pink here. So it's going to be 0 everywhere up here. Okay. It's first quadrant, so it's going to be 0 in this quadrant, 0 in that quadrant, and 0 in that quadrant. And the differentials have by degree 2 minus 1 for the first one, and R1 minus R. So once you get past the E2 page, all the differentials are going to be 0. Right, so you only have to look at the E2 page for this. Okay, so everything's going to lie on this line or that line. Okay, the spectral sequence lives right over here. Any questions on this? Good.
So this is a picture of the E2 page.
This is the E2 page. What's that?
I'm sorry, what was the 5 degree on this?
Oh, so dr, let me put it over here. So the differential dr has by degree R1 minus R. Okay, so when R is 2, it's 2 minus 1. So what you do is you go over 2 and you go down 1. Okay, so all the differentials here on this axis, they go to 0. So the possible non-zero differentials occur on this line. And then for higher ones, you have like 3 minus 2. So at that point, you sort of go over 3 and down 2, and then you're out, right? You get 0. So in other words, for this case, let's see. So E3 is going to be infinity. All right, any questions? All right, well, we'll be able to actually say more, so let's do that. All right. So here is the proposition. I like this because it's sort of, you're going to use things involving like the SL2 theory and in order to sort of get things for, you know, the entire group by using this sort of trick. So let alpha be a simple root and lambda be a weight. Okay. So let's see, I think I have more statements. So first of all, if lambda alpha check is equal to -1, then remember this is induction from B to G. This is always going to be equal to 0. Okay. B. If lambda alpha check is greater than or equal to 0, then we have the following. We have the HI of lambda. This is going to be equal to RI induction of P alpha to G. Induction from B to P alpha. And this happens for all integrals. Okay, so we can sort of identify this in we can sort of get rid of this part or just make this J be equal to 0. Okay. All right. So let's say we did this case. Of course, we have to do the other case too. And in the other case, we have a dimension shift. Okay, so let's do C. So if this is less than or equal to -2, then for I, we have HI lambda is going to be equal to Ri minus 1 induction from P alpha to G, and then we have to do R1. So these degrees have to add up because, you know, the spectral sequence, when you take the sort of diagonals like this, at the end, the sum of the terms has to be isomorphic to the cohomologies. So this induction can be P alpha of lambda. Okay. And the last statement, so E, suppose that lambda alpha check is dominant. So if the characteristic is 0 or the characteristic of K is P, and we have the Steinberg condition. This is equal to S P to the n minus 1. Okay. I won't put what the S is. It's the same as in the previous stuff. Okay. So then we have this shifting. This is HI plus 1. Okay, so remember over here that Ri induction from P to G of lambda is HI of lambda. Okay, so it's just a different notation for this. Okay, any questions on this? Okay, so let's see. Unfortunately, I have left myself with very little space to write here. Okay, so let's see what we can do. All right. Okay, so first of all, let's look at the spectral sequence. I'm going to erase this part up here. Okay. So maybe I can start using this space and kind of come on down. All right, so for part A, if I take lambda alpha check to be equal to -1, this means that R dot induction from B to P alpha of lambda is equal to 0. So that's by the previous thing. All right, so what happens over here? Well, all these terms are 0, right? So E2 is 0. So for every ij, E2 ij is 0. Okay, so 0 converging to this Ri plus j means that R dot induction from B to G of lambda. Okay, so we're just using the spectral sequence and the SL2. Okay, so good. So now I'm going to erase this next. And we did this. Okay, so now we'll do B. Okay, so now we'll do B. So lambda check 0. Well, what does this mean? Well, it means, first of all, Rj induction from B to P alpha is 0 for j bigger than 0. Okay, that's by Kemp's vanishing theorem. So what this says is that everything on this line here is 0. Okay? So the spectral sequence in this case only lies on this line over here. So it has to collapse. So all differentials coming in are 0, all differentials coming out are 0. So the spectral sequence identifies with this line. So this implies a spectral sequence, sometimes we call it degenerates. Okay. And so, so what do we know? We know that it's right. So E2 I0 is Ri induction from B to G in that case. Okay. But what is I0? It's precisely this over here. Right? So this is Ri induction from P alpha to G of induction from B to P alpha. Okay, and this here is just HI lambda. Guess we're done. Okay, questions so far? We're marching down and creating more space. Okay. Now, C, you kind of do the same thing for C. So if I take lambda alpha check, it's less than or equal to -2, then this implies that Ri induction from B to P alpha of lambda is 0 for I not equal to 1. Okay, by the previous proposition. So in this case, on this line you get 0. Okay, because when j, so anything on this line you get 0. Because when j is 0, this thing is going to be 0 in this case. And so everything lives on this line over here, right? And so again, the spectral sequence degenerates, and so your cohomology is just given by looking at the appropriate terms. So usually, if you want to look at the term involving 2, you have to look at this one and then this one and this one. Okay, so you can get some dimension shift. So again, spectral sequence degenerates. Ri induction from P alpha to G induction from B to P alpha. Whoops. No. So I got this wrong. This is I minus 1. This is R1, of course. So I think that's better. Which is precisely the statement. Okay, good. Questions? All right. So now, let's see if we can put D. I don't know if we have enough room. I mean, what I'll do is, are people done writing with this side over here? No. Yeah, I'm going to clear out more space by erasing all this.
The bottom part in part C for 1 sec.
Okay, sure. No problem.
Thank you.
Part C. Okay, so first of all, for D, have that lambda alpha check is bigger than or equal to 0. So now you can use part B. You say the following. So HI of lambda is equal to RI induction from P alpha to G of induction from E to P alpha. Okay. Now what we do is we use this condition over here. Okay, now by the corollary, we were able to identify the induction with R1 in the situation where we're either in characteristic 0 or we're in characteristic P with this kind of Steinberg wave condition. So this is RI induction from P alpha to G of R1 induction from B to P alpha of S alpha dot lambda. S alpha dot lambda. This is by the corollary. Okay. Now we had a formula for S. Well, let's see. Yeah, for S alpha dot lambda over here. So let's look at that for a second. Are you done? Is everything? Are you done okay with this? All right. So remember the formula. If you take S alpha dot lambda, I'll just rewrite it. This is lambda minus, okay, let me just do it this way. Lambda plus rho alpha check alpha. Okay. Now, when I take rho alpha check, this is always equal to 1 because rho is the sum of fundamental weights. So what I do is I can get lambda minus lambda alpha check plus 1 times alpha. Okay. Now that means that when I check with alpha check here, all right? So what do I get? Well, the first part I get lambda alpha check, right? And the second part I get minus lambda alpha check plus 1. Okay. And what do we get here? We get alpha check, which is 2. Okay, so what can we say here? So this should be less than minus 2, is that right? Two minus 1, right? So this, let's just write this out. This is minus lambda alpha check. That's good news, that's negative now, right? Okay, and then what do we have here? We have minus 2. Okay, so because this is positive over here, this is always less than or equal to minus 2. Okay. So now we're in the situation of the previous theorem or previous corollary. So this over here or actually we're in 5C. So this thing is equal to by part C, it's equal to H I plus 1 S alpha. And that proves it. It's kind of neat. We use the spectral sequence and we use these parts, and then we can sort of see that in order to sort of shift from I to I plus 1, we have to impose S alpha dot lambda. All right, any questions on this? All right, so the next thing I need to do is I need to introduce some more concepts to state the characteristic P version. Let me erase this. Okay, here now. All right. Okay. So for now, we're going to set so this is we sort of denote this as follows. So this is CZ, and then I want to put a closure bar. So a lot of times we call this the CZ bar. Sometimes people call it the sleazy bar. But anyway, in any case, we'll just call this CZ bar. All right, so let me tell you what CZ bar is. So this is going to be the set of all weights where these weights, when I translate up by row, so let's see, beta check. So this for all beta and phi plus. So let me write it this way. So there are two definitions. So this definition is if the characteristic of the field is 0. Now, what I want to do is I want to sort of put a roof on the bar. Okay, so this is kind of an open air bar. Okay, so characteristic P, there has to be a roof on top. It's less than or equal to P for all plus characteristic of K. All right, so let me draw you two pictures to show you the difference. So the first picture in characteristic 0 is basically the picture that I drew beforehand. Okay. So let's look at CZ bar. All right. So in characteristic 0, so let me just draw the A2 picture here. Okay, so this is minus rho down here, right? And then you have the other chambers, kind of look like this, right? So the CZ bar looks something like this. Okay, so it includes the axes here. And you have this region over here. Okay. Now, when you do this in characteristic P, we're limited, right? We have a condition where we have to have something on top. Okay. All right, so again, this is down to minus rho. And now what we need to do is we need to look at hyperplanes, which are P times things, okay, P times roots. So what we do is we get a picture which looks like this, with various hyperplanes tessellating the plane. These hyperplanes are sort of given by the action of the affine Weil group. Let me see that. Keeps on going. Okay, and then there are alcoves over here and over here and over here. All right. Now, in this case, you're bounded by this top length. So this alcove closure is this part down here. Okay, so this is the CZ bar in this case. So you're very much sort of bounded by something which is hyperplane on top in characteristic P. Okay, any questions on this? All right, so I have time to state now the Bott-Borel-Weil Theory. So this is proved by Anderson in general. Let me state it over here. So here's the theorem. So this is the Bott-Borel-Weil generalization. The proof is due to Henning-Anderson. All right, so it kind of goes like in characteristic 0. So the idea again is, when you take the dominant region over here, yeah, then what are we kind of worried about? Well, if you're in this kind of neutral zone, then you can get vanishing. So that's the first statement. So A, if lambda is in CZ bar, and lambda is not dominant. Okay, so again, you're in this sort of strip over here. Okay, so and your higher cohomologies are going to vanish whenever you translate around. Okay, so again, if you take this one, or if you're in the strip, you translate down here, down here, down here, down here, and down here. It's all going to vanish. All right. So don't park it, especially tomorrow. Okay. Second, now suppose you are in CZ bar and dominant. So in this case, you're down here and you're sort of in this region, kind of in this box over here. All right. So then, all W and W, the cohomology of W dot lambda is equal to H0 when I is equal to the length of W and 0 otherwise. This is for all loss. Okay, so for characteristic 0, this covers everything. Right? Covers everything. But it's clear if you take characteristic P, it certainly doesn't cover everything. So it only covers the translates, which are basically in this hexagon. Yeah. If you're up here, we don't know anything. Okay, so that's an open problem. So let me state this. It is open to determine the higher sheaf cohomology in characteristic. just even whether it's the vanishing or the non-vanishing. Okay, so that the sheaf cohomology is completely unknown. What is known? Well, it turns out that Anderson, these results are quite old. It would be nice to be able to go further on this. So there's sort of necessary and sufficient conditions for when H1 lambda is not equal to 0. So we actually know when H1 lambda is equal to 0 and when H1 lambda is not equal to 0. And there's a little bonus to this. We actually computed socle of H1 of lambda. Okay, so if you're given a lambda, the socle turns out to be irreducible. And so you actually know what weights appear in the socle, what irreducible appears in the socle. For H2, nothing, no. So again, this is a problem which is completely wide open in the field. It would be nice to actually have a criterion for when H2 is not equal to 0. But at this point, nobody knows. All right, so I guess I should probably stop here. And so I hope everyone has a happy and safe week. So we'll actually do the proof of author all day on Monday.
Second to H1 or tag,
For H1,
is that just H1 for Anderson's result?
this is one.